at any conference we visit or any university or research institution we'd ever see. We're excited to have the ACS Nano Rising Star lectures in this series too. One of the things we miss without traveling the world is the ability to meet new groups and to get their work out into the world. So it's wonderful to have this amazing forum for opening up this opportunity to our younger colleagues. And so, Alice, thank you for sharing ICANX with me and with, on behalf of all our speakers and our audience, thank you so much. So,
okay, welcome, Paul. And remember, yeah, every 2 weeks you will get up at 4 o'clock. Yeah,
so, yeah,
right. Yeah, that's really hard job, you know. Okay, now, Paul, the stage is yours. You're going to introduce Zhenan. Yeah.
Very, very
okay.
Well, I'm honored to introduce my friend and colleague, Professor Zhenan Bao, who's the chair and Keiki Lee, professor of chemical engineering at Stanford, and also a professor of materials science and engineering there. After, as you heard, she began her independent research career at Bell Laboratories. She's known around the world for her work in organic electronics and electronic skin, as you're going to hear today. She founded and leads the Stanford Wearable Electronics Initiative, eWear. She's been elected a member of the US National Academy of Engineering and the National Academy of Inventors. She's winner of the L'Oreal UNESCO Prize, among many, many others. And I want to welcome her, and we're looking forward to her talk, Skin-Inspired Electronics, Changing the Future of Electronics. Professor Bao.
Thanks, thanks very much, Paul, for the introduction. Thanks, Alice, for the for invitation to speak here. And I'm sharing my slides. Let's see, is it? Are you able to see it?
Perfect.
Oh, okay. All right. Okay. So today I'm going to tell you about the work we're doing in the group related to skin-inspired electronics. So a few years ago, when we first started to be able to put a electronic circuit to make them into the form factor like skin. This is the piece of semiconductor that we made at the time, and we made that into circuit, and it's a so-called unbreakable elastotronic transistor that can stretch with the skin without tearing. So we put out this article calling to bring on the body net and bring to the attention to the community that stretchable sensors, circuits, and batteries are about to change our relationships with electronics and with each other. So what we envision is a world beyond smartphones. We're in the era of smartphones, but transitioning into the era of we call elastronics regime, or the e-skin regime. We envision the future of electronics is going to dissolve into what we wear on our body, what we put on to our skin, and what we implant into our body. And this is going to be how we connect with our surroundings, with our friends, and communicate with our families. So in this talk, I want to kind of go back to, since the part of the theme in this series is also talk about kind of how we get to where we are. So I'm going to talk about what is electronic skin and how do we make them, and what are the potential applications, and give you thoughts on future outlook on where we see this, where I see this is going. These are two review articles that we put out. One was in 2013, quite a few years ago. But this shows kind of the evolution of electronic skin. So it's not a new concept. This concept has been around for a while. And quite a lot of the research also is fueled by the movies, science fictions, Star Wars, Terminators. But then really the desire to develop e-skin started with people wanting to put sensors onto a prosthetic hand to help people who lost their sense of touch to regain their ability to feel. And interesting to see that touch screen actually was invented in the 80s, but now only till maybe 10 years ago we start to have touch screen on our phone and the computer everywhere. I would say maybe the early e-skin would be this infrared e-skin that has sensors that can sense when a person gets close to the e-skin. Zhigang Suo just now mentioned Seeger Wagner. So when I was in Bell Labs back in the 90s, there was actually a sensitive skin workshop that was organized by Seeger Wagner, where we discussed about potentially build sensor networks that could be used for prosthetic hands. So probably that also stuck in my mind. And when I was exposed to the robotic cockroach that Mark Kukowski was building, all these came together that led to our work starting to explore the building of electronic skin. But it really wasn't until kind of mid-2000 there start to be more research activity in this area. Takao Sumiya's group in Japan started building organic sensor arrays, and John Rogers' group started to use inorganic devices to connect them with stretchable interconnects. Then after 2010, they're starting to have a rise in these research and basically maybe an explosion in the research in this area. So our first review article in 2013, there were maybe 100 references to cite, but 5 years later, there were hundreds of papers started are working in this area, and the progress has been really rapid, and now there are many exciting work ongoing. So for us, we really started with the interest of trying to understand how we can build electronics to mimic the sense of touch, and to help patients to regain their ability to feel using their prosthetic hand. So we started out by trying to take a look of how human skin actually function. So under our skin, under the dermal layer, there are actually these so-called mechanoreceptors, and there are mechanoreceptors, for example, slow adapting mechanoreceptors that respond to pressure, and fast adapting mechanoreceptors that respond to vibration and dynamic force. So these the combination of these mechanoreceptors, and many of them distributed into different regions of our hand and all over our body, allow us to be able to form the sense of touch. The mechanoreceptors, when they are stimulated or exposed to, for example, pressure, they will generate action potential, and the firing of the action potential is later transmitted to our brain and gets processed. So there already have been e-skin that, or artificial e-skin that have been prepared using mainly the flexible electronics, or developing rigid electronics, but also connected them with stretchable interconnects. But you can see that one of the challenges that we already start to think about early on is when we have millions of these sensors on our e-skin, how are we going to be able to process such a huge amount of information in real time, like our human? You probably all have seen this competition between the chess match between AlphaGo from Google and human. And here the AlphaGo can almost compete with human in the chess match. But if you look behind what's supporting the AlphaGo and also how much power that's consumed, you can see for AlphaGo, there's this supercomputer with thousands of CPUs and hundreds of GPUs and hundreds of scientists to develop the algorithm and consuming power in the order of a megawatt to be able to start to play a chess match with human. But for the human, we only consume some food and maybe a cup of coffee in the morning to stay up, to be able to fight with this machine-generated intelligence, and the power consumption is orders of magnitude lower. And the reason that our human brain is able to do that is because I mentioned there are these action potential that's fired when information is being given to us from external stimuli. So these are the spike-based intelligence. So basically, at these synaptic junction, these are where the spikes are generated, and many of them or are transmitted. And then all these information from different neurons can add in the synaptic junction and basically pre-process the information. And then in our brain, when we see an image, instead of processing this image line by line and pixel by pixel, our brain processes the image by learning, by making these connections between different parts of the brain, and through these patterns that's generated by the spikes. So that kind of processing now we call neuromorphic computing saves a lot of power. And so in our case, for e-skin, the way if we learn from human skin, similarly, the signal processing is not only we have the sensors, the mechanoreceptors that will be able to sense the external stimuli, but importantly, the stimuli through the mechanoreceptors, they're turned into spikes. And here you can see with increased pressure, the spike firing frequency becomes increased. And then these mechanoreceptors represented by these green dots, they come to the synaptic junction, and then signal, the spikes all come to the synaptic junction, and signal gets added, generate certain pattern. And then they further combine together and further processing take place. And then when this information transmit to our brain, basically there are different patterns are being transmitted to our brain, corresponding to feeling a surface with rough surface versus a smooth surface, for example, or soft object versus a rigid object. Therefore, in our case, we define the e-skin not just simply as a sensor and connecting the sensors and reading out all the sensors with transistors, like how we look at a display or process the display image, but rather our e-skin concept is mimicking exactly how our biological skin would function. That is sensing, performing sensing function, and be able to process the signal and generate these spike information. And the spike information will be pre-processed through signal processing and then interface with our brain. So with this electronic skin concept that we define as how we want to pursue the electronic skin, that means there are three very important components: sensing, signal processing, and the neural interface that we need to be able to learn how to build using materials, using methods we learn to build electronics. So we started out, this work was published 10 years ago, but we started out probably around 15 years ago, starting to learn first how we make sensors. We quickly learned that when we have a thin film, if it's a rubber material, if it's a thin film, it would be very difficult to take this thin film and have a reversible compressibility without having any hysteresis. So we came up with this design, the pyramid design, where the pyramid tip, upon exposure to very light force, can deform readily and bounce back and forth very readily. And this kind of pyramids can be molded, imprinted over very large areas, so on flexible substrates, and can also give us extremely high sensitivity that's similar to that of our human skin. Basically allow us to even detect the landing of a butterfly on the sensors. So this kind of design now becomes the one of the very common design concept for making all kinds of pressure sensor depending on the sensing range or sensitivity that is of interest, and they can be made into pyramids or pillars or rough surface, even just simple rough surface, or could be porous, or could be a line structure. And there have been all kinds of modeling developed by various groups to predict the kind of the sensor structures and also sensor performance with a particular design. So this becomes a quite well-established way of making highly sensitive, flexible pressure sensors. And then in addition to sensing just vertical forces, our skin is also able to sense when we hold for example, a bottle. When the bottle is slipping, our skin is able to sense the force that's not only vertically but also the sliding force. And that's because under our skin, we have these structures that looks like these bumps. So when the force is applied from different directions, then the mechanoreceptors on different sides of these bumps may get activated so that we're able to detect whether a slipping is taking place. So this can be also mimicked in our sensing structures. The more complex version also that we build also include these bumps so that we can start to sense pressure and the shear force. This is earlier we mentioned the research take a long time to get to where we are. So from the first time we invented the very sensitive pressure sensor to now actually putting it onto robot hand, it took almost 10 years actually to get there. But here you see the on this robot hand, the experiment to show that this hand can actually sense both pressure and the shear force is to place these ping pong ball onto this table where there are holes the ping pong ball can go through, so there's no shear force, vertical force to be sensed. And the pressure allows the hand to hold the ping pong ball without crashing it. But if it's encountering the surface that's without the hole, it will block the ping pong ball and sense the shear force. Then the hand will retract and sample the next location. So this is what the control is designed. When you sense the shear force, then it will retract and move to the next location. So very simple kind of demonstration of ability to sense the shear force. In addition to that, we also want to, when our hand grabs a object, where even without seeing it, we're able to tell whether we're grabbing a soft object or a rigid object. And to mimic that, we also learn from skin. Part of the reason we can do that is because our skin can actually stretch and deform. So when there's rigid object, there's less deformation compared to a soft object. So these are basically essentially string sensors. So we put a string sensor onto a membrane and combine with a pressure sensor. And then both are measured simultaneously. And then this deformation of the string under a given pressure will allow us to be able to determine the compliance of a object that the robotic hand is grabbing. So with the same pressure, the more deformation this string sensor experiences would suggest that the material is more compliant in that case, which can cause more deformation by pressing the soft material over this string sensor. So here, indeed, for these kinds of compliance sensor, if we expose it to glass, then the compliance that we measure is very low. But then if we expose to silicone, rubber material, we can see very strong response indicating very high compliance. And then if we have a material of different modulus, then the signal would scale correspondingly with the modulus of the material. So if the thickness of the material remains the same, and then the sensor can sense the modulus essentially of this material. So now that I talked about the sensors, Then the next part is the sensors not only have to sense the pressure or shear force or strain in terms of the absolute value, but for our brain to process the information, we need to convert the information into these spike-like signal so that they can be used to process very readily by our brain. So in order to do that, we mimic the, make the basic unit of artificial mechanoreceptor, basically using a small flexible circuit that is called the ring oscillator that can turn the pressure information into frequency information, basically those spikes. And by designing these sensors and small circuit to be in the right design dimensions, then we can have our artificial mechanoreceptor in the middle, this force sensing range and the frequency output can mimic exactly those of the biological mechanoreceptor as shown on the left. So now with these mechanoreceptors, so that would be the part that's highlighted into green. Then if we want to further process these information, especially as I mentioned, when we have many sensors sensing simultaneously, the processing speed and waiting for all the signal from each sensor to send to our brain, then it will significantly slow down the processing speed. So our biological system would combine these spike trains into synaptic junction and the pre-process before the information is further transmitted. So here, this combining the artificial mechanoreceptors and synaptic junctions will allow us to make an artificial nerve. So this is what we did. And here, basically, the synaptic transistor are used, and the electrode here is used to control the ions going in and out of the semiconductor, which will be able to process the spike information and retain some of the information. So here what you see is if we have two sensors, one is sensing force at 20 kilopascal. It puts out a frequency pattern as shown on top. And then with a higher pressure of 80 kilopascal, the frequency is higher. And then when these two signals are all input into our synaptic junction, then we get a combination of these spike trains in terms of the amplitude and the frequency pattern. And then this would be the pattern that we can teach the synaptic junction to learn, or teach also the algorithm to learn to be corresponding to potentially a certain object, or it could be corresponding to, for example, here is a shape, and then in the synaptic junction or the synaptic transistor, the pattern of the information from this frequency signal that's combined gives this shape. Then we can teach the device to learn that this corresponds to the shape of line, or can correspond to the shape of this Braille pattern that's being activated. So instead of scanning all the devices line by line, especially when we have many of these sensors and different patterns, then these kinds of pattern learning kind of approach or the neuromorphic approach would significantly accelerate the readout or processing of the information. So now I've shown you that how we can kind of build the basic element of the artificial mechanoreceptor and how we do simple signal processing. And this is a very kind of early version of such kind of artificial mechanoreceptor. Started out with one single pressure sensor, and then we believe as we learn more from how to build these devices, then we can start to make them more complex. But at the same time, we also ask the question, what else we can learn from the skin other than how we sense information, process information. Actually, as a chemist by training, I constantly look for inspiration for designing new materials. Actually, when we started building these sensors, we start to realize that skin actually is also a wonderful material that is not only flexible, but also stretchable, biodegradable, and self-healable, all at the same time. And these are the properties that our electronics currently still don't have. But if we're able to make electronics materials that combine all these properties with the sensing functionality and signal processing, then potentially we can make the our artificial mechanoreceptor. The first version was only flexible, but then as we develop new electronic materials, we can start to make them stretchable, self-healable, and biodegradable, just like our human skin. So that becomes one of our major research directions in terms of materials development in the group. But the biggest challenge that we immediately faced was that many electronic materials, even polymer materials, plastics, can also still crack very readily when a small strain is applied. And this has to do with being able to transport charges. We require these materials to have certain crystallinity, which make them to become more brittle. But our vision is to to fundamentally develop new materials so that we can solve this problem and use these new generation of electronic materials to develop to build our e-skin. There are of course, a number of approaches to solve this problem. The string engineering approach is an approach that has been pioneered by Roger's group and Huang's group. Now they're both in Northwestern, and basically connecting the rigid components with these stretchable interconnects. And this can make very sophisticated electronics nowadays, just by taking even commercial electronics and connect them with stretchable wires. And also, Zhigang is one of the leaders in understanding the fracture mechanics in a variety of different materials, and through the modeling, come up with ways to help these materials to become more mechanically robust. For example, also taking advantage of fracture in these crack gold to be able to make conductive material stretchable. But we decide to take an approach from as an organic and polymer chemists to, instead of using existing material, but rather look at how we can design material from molecular level and be able to realize all the skin properties without compromising the electronic property. So that's the goal for our research. And the key concept that we use to come up with these new generation of materials that can have the stretchability, robustness, and even self-healing property as human skin is to take these conventional rubber material where the polymer chains are linked together by covalent bonding, where when the covalent bonding breaks, if the material is subject to very large strain, then become irreversible damage, but rather turn these covalent cross-linking sites into dynamic bonds that are reversible under room temperature or elevated temperature. And the breakage of these bonds helps energy dissipation and allows the material to have increased the total fracture energy. And also the reformation of these bonds allows the material to self-repair themselves, to recover to their original mechanical property and electronic property. So that's the concept, that kind of concept was the basic guiding concept for us to develop various generation of different electronic skin material. Our first generation is a self-healing electronic conductor that can heal and self-heal when even when there's a crack and be able to sense pressure, sense strain. And then since then, we advanced our understanding in the chemistry and we have a number of different versions of the skin. This is a super stretchy and self-healable skin that allowed us to make one of the first self-healing actuator that using this material. And then with further understanding of the design, we can use very simple molecular structure, but be able to realize extremely tough elastomer that even with intentional damage like this notch that's cut, we're still able to allow the material to be able to under extreme strain without breaking. So taking this concept then combined with our learning over many years on designing high performance charge transporting semiconducting polymers, then we can combine these concepts into our semiconductor design and coming up with the first generation of semiconductor that allow us to build the first intrinsically stretchable transistor, where all the components in this transistor layer are built with intrinsically stretchable material that we develop in the group. And then these materials can be further developed to not only to be stretchable, but also be able to sense. So this is the newer version of a string sensor, sensing electronic skin that has many of these transistors built in an array and can read out the shape of the object. So without going into all the materials we developed over the past decade, through the hard work of the students and creativity of the students, now we have a collection of electronic materials ranging from conductors to semiconductors, even substrates that are, some are stretchable, some are self-healable, and some are even biodegradable. So with these materials, now our new electronic skin or these transistors that are components for making electronic skin takes the new form factor they are not only flexible, but you can see under extreme strain, the red curve here is the output from these devices. They can maintain without degradation in the electronic property, even when the material is subjected to extreme damage. And very importantly, one of the parameters to characterize these materials is the charge carrier mobility and the speed they are able to operate. And as a reference, the amorphous silicon transistors are being what's currently used for our laptop displays and many of the electronics that we use. They have the charge carrier mobility in the order of 0.1 to 1. And currently, our stretchable semiconductor can already reach and go beyond that performance. And we're starting to enter into the regime with some new generation of materials we're developing, enter into the regime of polysilicon. So that means these materials can really start to allow us to build some serious electronics that could actually provide the complexity that's needed to build our electronic scheme. So with the materials, in order to get to the electronic scheme, then the fabrication method is also crucial. So this, we have spent, again, quite a number of years to figure out how do we pattern the material into small structures, and then how can we build all these circuit blocks that can function well and under various strain. So now, with the hard work of the students and postdocs, now we're able to fabricate not just one or two transistors, but rather thousands of these transistors. And these transistors can be made into these tactile scheme where we have, in this case, we have 10 by 10 arrays, 100 transistors, together with tactile sensors, so that we can sense now this ladybug, the location of the legs of this ladybug, and to make much more sophisticated e-scheme. And what's more important is that now with the development of materials and the fabrication, we're really at a stage that we can start thinking about completely reinvent the electronics with these new development. Our current electronics is still rigid and brittle, but with these new materials, we can imagine the new generation of skin-inspired electronics that are soft and conformable. And the advantage of doing this is that with closer contact with human, and that's where the information is, then we can have minimum signal attenuation because of the movement, and more robust for these electronics under deformation, and also minimum invasiveness if we make the implantable electronics. So essentially, we are now able to build these electronic scheme that has all the components, functions, the sensing, signal processing, as the human skin, and also have the form factor like human skin. So you can see that we can, this is really resemble very much of the wearables that we are building today. So the next missing part is how do we interface these electronics with our human body? That is the biointerface question. And here also making an analogy between the skin and what we build now as the basic artificial electronic system. So here we have again the sensing we draw earlier in a different way, but if we use the circuit design blocks, then we would have the sensing front, actuation, and then in the middle, these are the circuits we're building also with the skin-inspired materials that can perform digitization of the information, amplification, and pre-processing of the information. And then finally, all the information go to the central processor, or this could be direct interface with our human body, where our brain is the processor. So these new stretchable materials and the fabrication method now can allow us to build the basic circuit blocks from NOR gate, AND gate, amplifiers for amplification of electronic circuits information, sensing information, and also digitization of the information. So all the blocks are there. So that's the signal processing part. And with these circuits, we can also design, using circuit design, to compensate for the issue of movement and be able to sense information without being affected by the movement. So as I said, these are a lot of new development. But the last piece that we need is the biointerface. And here, the biggest challenge we think that the current rigid electronics are facing is the mismatch at the interface with the hard and the soft tissue. There's a mismatch. And then the dynamic movement and also the changing size in the biological system. These are the areas of challenges that current electronics cannot solve, but rather could become the opportunities for our future skin-inspired electronics. Of course, one can make the rigid electronics to be smaller and make them to be ultra thin to be able to conform to biological system. But still, their rigidity is something that is difficult to overcome. And in this case, using conducting materials not only give us the softness compatibility with the biological system, but also at the same time, these conducting materials have been found with their special transporting mechanism of transporting both electrons and ions, result in very low interfacial impedance when they are interfaced with biological system. So with the coating of this conducting polymer, it was found by many groups now, but David Martin's group was one of the earlier ones to start looking into this. The impedance compared to metal could be lowered by several orders of magnitude. And what this means is that the very, very weak signal from biological system can be read if we coat with the conducting polymer at the interface. And a much lower voltage can be used for us to read this information. So our goal is really to make these conducting interface to be high conductivity and also extremely soft at the same time. I see that I'm starting to be short of time, so I won't go into detail. But the key is to really control the ionic interaction in these materials so that we can promote the conducting pathway to form in an interconnected way in the matrix of ionic matrix that forms this gel state, which gives us the conducting hydrogel, but also maintain very good conductivity pathway in our material. So here with the development by the student now, such kind of conductive material that from understanding of how to tune from molecular level, then now we have these are electrode patterns that are patterned, very high resolution. That's why you cannot really see individual ones. They're in the micron size with high conductivity and almost transparent, and also have the low impedance with biointerface. So these are now the electronics interface that now we start to explore them for connecting our sensors and electronics to stimulate the nerve, to measure electronic signal from the heart or from the brain, or to read information from our brain. So that forms the soft interface that's very important to allow us to collect the information necessary. I'm going to start to skip a few slides as we're running out of time. So then I talked about all the components now, and the application we foresee with these electronic skin going towards the future is really to take advantage of their ability to conformably interface with the organ and biological system, and be able to sense and process information all at the same time. So for robotic applications, taking advantage of the stretchability, and for making wearables, sensors that can be reconfigured, taking advantage of the self-healing property and the reconfigurability of these materials and the conducting interconnect. And finally, well, at the beginning, I mentioned the body net. And finally, more recently, we made the first version of the body net, where the sensors are made with entirely stretchable materials that are placed all over the body. And then we place the electronics onto the clothing we wear, so that the information collected from different places of the body, where when you have many stickers, you can place where you want, and the information is all read, and through this central Bluetooth communication hub, it can be communicated to all the information to our computer or cell phone. So then we can gain the information about the movement of not just how many steps you take, but rather whether your hand and the legs are moving at the same time, or what's your breathing and your pulse, everything all measured with these stickers. They can be made very small and thin for implantable devices. These are implanting these body net sensor into the brain to measure intracranial pressure, and wrapping around them onto the artery to measure the blood flow. So to summarize here, I give you a very quick overview of our journey. Basically started from trying to mimic the sense of touch, to lead to us developing the concept of the biomimetic electronic skin, to developing a new generation of electronic materials. And now we're at a stage where all the components that we need to realize this science fiction image of the future wearables, where all the components can already started to be realized using these components. And of course, the future is to put all of them together and see if we can really realize this dream that's shown on this Time magazine. But where do we go from here? What we are very excited about is really to see how we can interface this electronic skin seamlessly with our human body. And the connection with the human body, I talked about putting probes into our body. But how about to actually grow these connections directly from where we want them to be? So this is the concept that we're really excited about, and I see as a future of how we connect our electronic skin with specific neuron cells. That is to use genetic targeting to target certain cells, neuron cells, so that they can initiate the growth of conducting polymer only onto these neuron cells. And then these conduction pathways can connect directly, hopefully, with our sensory skin. And now we can show already these conducting paths, conducting polymer can be grown on neurons, on brain slice, and even in live organism. So I see the future outlook is really how we can think about merging electronics with biological system. So I would end there and thank funding agencies and especially collaborators who give us a lot of inspiration of the work we do. And most importantly, the students through their creativity and hard work. This is how we are able to get to where we are today. And I look forward to continue exploring and inventing with the students. And again, it's a pleasure to be here. And thank you everybody for joining this. And I'll be happy to answer any questions you might have.
Terrific. Thank you so much. That was an amazing talk. I think Alice is about to put up some of the questions. Here we go. The first one is, Professor Bao, a very nice talk. Thank you. For the e-skin you mentioned, can you use soft or rigid materials? Is it possible to identify different materials? I'm not quite sure what they're asking there, but maybe I'm thinking about mechanical.
Yeah, I guess the question might be for the e-skin whether we should use all soft materials or rigid material or combination of both. Well, our plan is to potentially, in our case, if we want to make the take advantage of the stretchability and the self-healing property or biodegradability of new materials, then this could enable a different kind of e-skin that might be fabricated with rigid material. So it depends on the application that one is interested in. It's possible to make e-skin using either one of the material or most likely hybrid approach might be the approach to realize all the requirements for a particular application.
Very nice. Next question from NKU Lin. You mentioned work of, I guess the question is, can you detect a butterfly on the electronic skin, and really something about, what's the sensitivity of the response? I think you addressed that with the ladybug to some extent. And then another question is, what happens if a nail goes through the electronic skin? does electrical performance, electronic performance change, or does it get restored?
Mm-hmm. Yeah, so for the butterfly, the weight of the butterfly is in the order of tens of milligram. And landing in a small region of the skin, the pressure generated is in the range of Pascal or tens of Pascal. Actually, our human skin is of course able to sense that kind of pressure. And for the e-skin, we found that we're able to detect the weight as small as a few milligram in weight over a very over an area of 1 centimeter square. So that corresponds to a few Pascal of pressure. So certainly the e-skin are able to detect the landing of a butterfly. And then for the nail piercing the electronic skin, indeed we have we have done some experiment. First, in our case, we try to design our material so that the nail cannot penetrate through, and because the molecular design can make the material very tough and very robust. But even if under such high strain, of course, if there's a breakage, a hole is generated, then the electronic pathway will be broken. Then electronic signal will be lost in that particular region. But if there's no piercing through, then the material under extreme strain, they, as I showed in one of the videos, they can still function as normal, and also through circuit design of combining the multiple transistors together, then through these kinds of circuit design, we can compensate the signal variation due to the deformation, and then be able to read out the e-skin signal with as little error as possible.
Actually, I have a related question while the next one comes up to the first part. Do you build in electronic crosstalk in your receptor network, or do you just count on a mechanical sort of the cross-linked network on which the receptors sit?
So for the receptors, we have they are individual receptors where we have one sensor, one pressure sensor, and then one small circuit ring oscillator to convert the sensing information into digital information. And then this unit will input into our synaptic transistor. And then multiple of these units can input a signal into the synaptic junction. So that's where the signal start to cross with each other and get added into the synaptic junction to generate a pattern of the signal, which correspond to the shape or could be the roughness of a surface. So that's how we connected the electronics. There's another version of electronic skin, the earlier one that I showed, that's made by Takao Sumiya's group or Ali Javi's group. That's based on a active matrix type of sensor array. So no spike signal, and basically signal processing is similar as for our display. You scan line by line and column by column to scan each individual sensor information. And then that will generate an image similar to what we see on the display. That will give the resolution, high resolution, and also mapping of a shape. and the dynamic change of how the shape changes, but it consumes a lot of power to process so much information. So if we imagine building a e-skin that similar to our human skin, where there are going to be billions of these sensors, then the signal processing is going to be become a huge issue, and power consumption is going to become a huge issue.
Interesting. While we wait for the, oh, here we go. Dear Professor Bao, impressive. In your talks, most of the sensing parameters are physical signals, but in our skin and our body, there's also biological information, and it's chemically related. Do you try to take those, record those signals and take them into consideration and integrate them as well?
Mm-hmm. Yes, chemical signals are very important for detection, and there have been a lot of development in the field. Paul, your group have shown dopamine sensing and different neurotransmitter sensing using transistor devices. So in our group, we are also developing related sensors, but in a skin-like format, stretchable and biodegradable. And these chemical sensors can really allow the e-skin to not only sense just the electrical pulses from the brain, and also the chemical information. And the chemical information is what's modulating our behavior and our thoughts. So combining the physiological information and electrical information as well as the chemical information is going to make the even more powerful e-skin in the future.
On the last part that you showed, you were integrating directly into biology. So what's your dream about what'll happen, what you'll be able to do there? Mm-hmm. And then we'll get to the fourth question. Sorry, I wanted to slip that one in before we ran out of time.
So for the my vision is really now we can build this sheet of artificial skin, and then next, how do we connect to our body and have the information go into the brain? And especially in the case for a patient who had a skin wound and lost the sense of touch. So for the information that we gain, then the sensor information will have to be transmitted through specific nerve, so that then our brain knows whether this information, which region of the body this information actually comes from. So what I envision is if we can grow these electronic connections from our body and connect selectively by itself to the electronic skin, wouldn't that be nice? So that's how kind of also mentioned earlier by Zhigang and also Gang, the importance of colleagues, inspirations from colleagues. That was a discussion with Karl Desroff, who is one of the pioneers for optogenetics. And that conversation led us to start thinking about how to make conducting connections genetically targeted to the nerve, so that we can connect the right sensor with the right nerve to get to the brain.
Terrific. The next question comes from Wang from Beda. As you said, humans can complete the workload of an entire room of computers with just a cup of coffee, and I brought one along for that purpose. What research has been done on the energy supply for your electronic skin, and can the power consumption of the device be brought down to the level of human energy consumption?
Mm-hmm. Yeah, so for the reason I mentioned a little bit, the reason why human brain can process information by consuming so little energy is because our biological system have developed all these signal processing kind of methods that doesn't require us to be constantly, for example, we are not constantly sensing unless the information actually triggers us. Or if we stare at a certain image for long enough time, then our brain will start to take a break unless there's movement. And then we start to know, oh, okay, there's change in this image. And also all kinds of pre-processing of signal and pattern recognition and pattern learning. So all of those methods contribute to the low power consumption of the human brain. So that's why starting early on, when we start to define our e-skin concept, we define it using by mimicking how our brain process information, and by defining the e-skin of not just having the sensors and the transistors to switch to read out the information, but rather having a small circuit to generate spike-like information, similar like how our nerve system would transmit signal and process signal. So that's a very important aspect to in the future to lower the power consumption of these e-skin.
Wonderful. The next question is from Zhehua, also from Beida. They ask, are the signal sensing, processing, transmission, and human-machine interface already compatible with the human body, or is this really set up to work for robots?
Our signal pattern in terms of a spike train, that's the type of signal pattern that our nerve can transmit, and that's the pattern our brain would process. So we are able to generate these patterns with the e-skin, but of course we still need to learn what pattern to generate that our brain will interpret as, say, sense of pain, or a difference in temperature, or the roughness of a surface. So these are requires one is learning how to generate the electrical signal that our brain can understand, and the other is to understand what kind of signal our brain needs as the input. But of course, our brain also has plasticity. So we, to a certain degree, we can also train the brain to understand the signal that are coming through, even though it may not be the conventional signal that we're used to. With training, our brain can learn.
Okay, Paul. Yeah, we still have some time, so we select the 3 more questions. Okay, we have 3 more to go.
Again?
Yeah.
Lovely. Yes. So the next question is there a precedent for applying e-skin in underwater environments, and could underwater robots use these flexible sensors?
Yeah, definitely. Some of the sensors that we built, we have already implanted them inside the animal, and that's of course under aqueous condition, but it's those kind of sensors are not as sophisticated as what's needed for robots. But what I want to say is the materials can be used, and sensors can still be used under aqueous environment. And for robotic application, there are also the circuits are going to be involved. So encapsulation would still be very important for these e-skin for underwater applications.
Yes, very good. And the penultimate question, what role do you see for graphene and other 2D materials in the field of flexible electronics?
Graphene and 2D materials being ultra thin allow them to have very, very good flexibility, and potentially they can make electronics to be essentially a few atomic layers thin. And that will allow these electronics to conform into the wrinkles of skin and the folds in the brain. But of course, these materials are not very stretchable, or not essentially not stretchable. But there are strategies to also make them stretchable. A few years ago, we published a paper where we discovered that if you transfer graphene layer by layer on top of each other, then the pi-pi stacking between the graphene is not as strong as in the case of a nice piece of crystalline graphite. And in that case, there can be some sliding between the graphene layer. Then the stretchability of the graphene becomes much improved, well, from 5% strain before cracks is formed to maybe 50% strain. Using these kind of stacked graphene. And also people have made wrinkled graphene or 2D materials, taking advantage of the ability for them to form extreme bending and folding without changing electrical performance. So that's another potential strategy to make stretchable electronics using these remarkable materials.
And then the final question is, how are the mechanoreceptors powered?
Oh, for currently, the mechanoreceptors are powered in two ways. So one is wired with battery. And in that case, well, in the e-skin on the hand, you do not see the battery behind it. So the current battery are still mostly the coin cells, or at most the flexible battery. So we see that as one of the very important development that's needed for e-skin to be truly conformal and skin-like. So there are some activities around the research community and also in my group in developing such kind of stretchable batteries. Another approach is the BodyNet approach, where we separate the sensor and the rigid component, the battery, into two parts. And the sensor is powered wirelessly by the battery and the external reader and power source, and read out the information wirelessly. And in that case, then the sensor can be, and the tag that's placed on the body can be entirely made of stretchable materials and with no rigid components. But there are still limitations. There's a certain range the reader can work. So the reader has to be very close to the sensor in order for this to work. And also the relative position of the reader to the sensor, also there's limitation. They cannot be too far away, and they cannot be have too much movement that the reading may become inaccurate. But the power source is something that a very important further development area.
Perfect. And finally, we'd like to thank you. And this is something that Alice will get us all in person when that becomes possible for us to meet together. But in the meantime, here's an electronic version of the plaque that'll come for being one of our ICANX speakers. It was a fantastic talk with well over 300,000 attendees, which might be a record for you. Maybe you've had more in attendance for your talks before. And of course, all the talks are available later and also transcribed into Chinese within about 2 days for those who'd like to read along that way. So thank you and Professor Gang Chen both so much for this fantastic program today and your inspiring work. And we're looking forward to what comes next from both of your labs. Thank you.
Thanks. Thanks very much for having me here, Paul and Alice. And nice to see Paul and Zhigan.
Okay, thank you very much. Yeah, Paul, yeah, wonderful job and Zhenan, as always. The talk was amazing. There are too many questions. I selected, a few more to you. Now, yeah, we came to the end of today, and this was next week. We will have two faculty members here, one from Hong Kong, University of Science and Technology, Zhi Yongfan, will talk about biomimic of the eyes, and Amani was from USC, will talk about something, transfer from lab and to the whole world, to save the world, especially some technology using for the COVID-19. And Paul will be the chief editor and a chief leader on this stage next week. So we're looking forward to next week. And yeah, we still have a bunch of our top scientists to go to put on our ICANX talks in the following months and years. So please stay with ICANX talks. And I have one more thing to announce here is in Chinese. Sorry about Paul, but it is in Chinese because it's a Chinese event for the graduate students. We have a top scientists at ICANX talks. We have rising stars in the young faculty, but we don't have a stage for the students. So I built up a new stages for the students, graduate students, yeah, to play like, the soccer game, yeah, by rounds, weeks, yeah, several weeks, they win a title, they win medal, you do presentation to be a team. So I built up some a new stage since next Monday, we have 3 weeks for the young students, not young scientists, young students, yeah, to practice and to promote the technologies. Yeah, so that's next Monday. Yeah, we start at 7:30. So stay with us. And so, yeah, see you next week on ICANX Talks. We're looking forward, to many, many new topics. Okay, that's the end of today. See you next week. Bye.